Newton's first law states, if the resultant force acting on a particle is zero, the particle will remain at rest, if originally at rest, or will move with a constant speed in a straight line, if originally in motion. So essentially, if we don't act on something, if we don't add any new forces, if something's already in equilibrium, it'll stay in equilibrium. And so when we see that in notation form, we say that resultant equals the sum of the forces, and that has to equal zero for something to be in static equilibrium. So if it's in equilibrium, if we sum our forces, they have to equal zero. And if we're looking at in 2 dimensions, we'll see later with 3 dimensions, we have additional equations. But in 2 dimensions and for a particle, we can sum the forces in the x direction and they have to be zero, and we can sum the forces in the y direction and they have to be zero. And so we'll look at a couple examples here and look at drawing free body diagrams of a particle. So again, a particle is, it's not necessarily an infinitesimally small thing, but generally, in our case for statics here, it means that all the body can be just represented as a single point, and we can idealize it as a single point. So we'll look at a couple examples here. We have this steel bracing connection here with a gusset plate and a column and beam and brace all coming together at a single point. Right here we have this point where all of the lines of action of the vectors intersect at that point. And so we can use that point as our particle for drawing our free body diagram. So we can we draw it just as a dot, and then we add our forces to that, and we add them in the direction in which they're applied and add them as vectors. So we have, in this direction, we have T B, the tension of B. In this direction, we have the tension A. Straight down here, we have the tension of C, and then in compression here, this brace is pushing back up. That would be TD. So tension is a pulling force, and compression is pushing, and we show our vectors as such. So if the vector is pushing, then we know it's compression, and so on. If we don't know whether something's in tension or compression, we always draw it in a positive direction. So we draw it as tension, and then we find out if later if we're correct. So we need to put in here any kind of angles that we have. So the TA, TB, and TC are all either horizontal or vertical, but this angle we need to add our 40 degrees as the angle of that of where TD is applied. So now if we said, like, let's say that TB here has is 15 kips. If we know that's 15 kips and TA here is 8 kips, we can use our equilibrium equations to determine what the values of the other forces are. And so let's try that right now. So we know if we add, we'll show it like this. So we're going to sum forces in the x direction, and we know they have to be zero. And we'll put our little sign convention on here. I'm going to say that to the right, we're going to consider that to be positive, and I'm going to add my forces here. So, and by the way, a kip is 1,000 pounds. So a kip equals 1,000 pounds. And it's just a notation we use in U.S. customary notation. So we're summing our forces. So we have TA here is in a negative direction, and we have that is 8 kips. So negative 8 kips. We have TB is in a positive 15 kips. We add that. And then TD, we don't know what TD is, but we know the angle there, and we're only adding the x component, the component of TD in the x direction, which would also be headed in a negative direction, and that would be TD times the cosine of 40 degrees. And TC, there is no component at all in the x direction. It is all in the y direction, so there's nothing from that. So this is going to equal 0. So the only thing we don't know is TD here, and we can just use our calculator and our algebraic knowledge to find out that the tension in D is 9.14 or 9 1400 kips. So there we have TD. Now we can sum forces in the y direction and equaling 0. And we have TC, and that would be negative, because I'm saying that up is positive, so negative TC. And then we have positive, because this TD would be in the vertical component is up, so plus TD times the sine of 40 degrees. And that's it. The other two are all horizontal, so they won't add anything here. And so that has to equal 0. We also know here that TD equals 9.14 kips. So TC would equal 9.14 kips times the sine of 40 degrees, or 5.9 kips. So TD is 9.14 kips and TC is 5.9 kips, given the fact that the tension, or that force in A is 8 kips and the force in B is 15 kips. So that's how we use our equations of equilibrium.